Hey, good evening, everybody. Welcome to the Marston Exploration Theater. Glad to see a group here tonight. And then we also have an online audience as well. So I'm announcing officially here, hi, online audience, and welcome. I'm glad you're here. What we're going to do, I'm actually Rick Alling. I'm the manager of outreach programs for the School of Earth and Space Exploration, especially here at this building. The Marston Theater actually celebrated its 10th anniversary this morning. We had Susie Marston, our philanthropist and the original donor. She was here with us with a group of fifth graders, and it was really a great time. It was fun to do and fun to remember 10 years of different programming and different kinds of things in here. You're attending a thing called the New Direction, New Discoveries lecture series, something about that. It is actually something we started about, I guess, 8 or 9 years ago. We've been doing this ever since, with the exception of the COVID years. And so the New Discoveries lecture series includes one event every semester, so that means two a year. And tonight we're going to be welcoming in just a moment Dr. Evan Scannapieco and Dr. Ed Buie. I'll give a little bit better introduction of them in a moment. For those of you online, you're watching in a webinar format, and so we do encourage you to ask questions, but you'll need to use the question and answer button, not the chat button. So the chat is disabled for tonight. Use Q&A, and we will bring those questions forward at the end of the program. And then for those in the audience, same thing. If you wait until the end, we'll have a chance for you guys to ask questions as well. When the audience questions, will have to get to a microphone. So we'll have a student and myself and Kim. We'll be kind of running microphones around the room so you can do that. We are actually doing the program in two halves, and so Evan will be first. Ed will be second. Ed is going to be presenting from online. He's in Poughkeepsie tonight, so he'll actually sort of be online on the screen, but that should work out very nice. So I just want to introduce the two players tonight. Evan Scannapieco is a professor at ASU in the School of Earth and Space Exploration. He earned his PhD in physics from the University of California at Berkeley. And after postdoctoral work at Acetri Observatory in Italy, Paris Institute of Astrophysics, and Buie Institute of Physics in UC Santa Barbara, he joined ASU in 2007. His research is focused on feedback from active black holes, the first stars, galaxy outflows, and supernova and turbulence. Ed Buie, the second, is an assistant professor of astronomy at Vassar College. He earned his PhD at ASU right here in this past spring. He worked with Dr. Scannapieco, investigating the role of turbulence in galactic halo simulations using MAYHEM, which is a modeling code that tracks ionization states of many elements under extreme conditions often found in astrophysics. And that really brings us to the program tonight. It is the invisible halos of galaxies. And please welcome to the stage Evan Scannapieco. Thank you.
Hi, everyone. Is this on? Yeah, okay. So thanks to all of you who came out here in the Marston Theater tonight, and all of you who are joining us online to hear a little bit about the stuff we've been doing. In regards to invisible halos of galaxies, I'd like to start just a little bit closer to home. Here's the sun, right? We live in the valley of the sun. Sometimes it feels like it is very, very near to it. We're almost on the surface of the sun, but it's not true. It's 100 million miles away, more or less. And so that's about 8 light minutes. And what that means is, any light that gets us from the sun takes about 8 minutes. If the sun were suddenly to disappear, don't worry, that won't happen. Then we wouldn't know about it. 8 light minutes away. If we zoom out a little bit, here's the solar system. It's not to scale. I think I have a pointer here. Right? So the online people won't see. Try not to rely too much. But anyway, so you have the inner planets here: Mercury, Venus, Earth, and Mars. The distance from the Earth to the Sun, 8 light minutes. 8 light minutes. We call it an astronomical unit. We define astronomical units, and if we use those same units, Mars is about 2 times 2 AU, and Jupiter is about 5 times as far away from the Sun as we are. And then you go on out to Pluto, which is about 40 astronomical units. 40 times 8 is about 5 hours. These pictures that you may have seen from the horizons, like of Pluto, it took over 5 hours for the messages to get through. And that's on the scale of our solar system. So imagine we were to do something like this. Let's imagine we made a little model. We put the sun here at the. Sometimes I do this in my classes. I can put, a sun, blow up sun here, and lay out the planets. And we have the inner planets inside of this Martian theater. So Jupiter is there in the back. If we did that, this is where the other planets would be, the outer planets would be. It was not officially a planet there. And so I have a question for you. So let's say we had this scale where we've shrunk, the distance it takes light to travel over 5 hours to the scale of the parking lot in the rear. Where would the nearest star be on such a scale? Would it be over on McClintock Drive, the next big road about a mile over? Would it be somewhere over in Mesa? Would it be Apache Junction up near the mountains that are in the east? Or would it be way over in the eastern part of the state? Who thinks it's A? Go ahead and just pick it. Raise your hand if you think it's A. No? How about B? How about downtown Mesa? Anybody want to go for that? How about Apache Junction? Bakersfield, that's pretty far away. How about eastern Arizona? Everybody pick that? So here we are, and the actual answer is Dallas, or a little bit east of Dallas. Right? So the jump in scale when you go from our solar system even to the nearest star is just huge. Okay? It took light 5 hours to get from Pluto to us, but the stars, it takes tens to hundreds of years. So those are the stars that you see with your eyes. So if you're looking at stars in the night sky, one of them maybe you'll see, around, I don't know, maybe 10 years ago. Or another one would be like, oh, that was when I was in high school. Another would be, oh, that was from when they founded the United States, right? Or maybe, Columbus. So they're on tens to hundreds of years. The time it takes light to travel from the stars that we see in the night sky with our eyes. The galaxies are a leap further, right? Galaxies are a collection of millions to billions of stars, actually billions to trillions, millions to billions of stars going around. Here's our nearest large neighbor galaxy, Andromeda. And this is made up of so many stars, we can see it at a distance that's just enormous, right? That's at 2.5 million light years. Now we're seeing this thing not as it was 5 hours ago, or even, 100 years ago, but as it was 2.5 million light years ago. Well, this is pretty neat because in a way it's giving us a time machine. This is a nearby galaxy. We're seeing it as it was 2 million years ago. And if we look at further and further, we can see things as they were further back in time. Here's a galaxy that maybe you saw this one in the news yesterday. So this is a pair of galaxies that was observed with the Hubble Space Telescope and with the Webb Space Telescope. It was by a team right here at ASU led by Roger Winhorst. And you can see this galaxy is in front of this one, right? You can see dust and things. And this closer spiral galaxy lit up by the one behind it. These are about 700 million light years away. Here, sometime not too long from now, I'll be able to show you, a deep field taken by the Webb, looking even deeper than this one. But for now, this is the deepest image that we have of our universe, taken with the Hubble Space Telescope. It shows galaxies out to 14 billion light years. And so, if we compare the nearby galaxies, the closer galaxies that we have in this image, to the ones further away, we can reconstruct the whole history of how things change. Yeah, it's like doing history, but you can see it with your own eyes instead of reading it in a book. But there's one catch. So, how are we going to do that? Because tell me which galaxy is further away. Which one? How do I know distances. Maybe you want to pick anybody. I mean, so maybe I might pick the small one, might be further away because it looks tiny, but it's really, really hard to know. So we have to have some way of figuring out what are the distances and things so we can reconstruct that history. Let me tell you a little bit about how we do that, and then we'll get to these invisible part of it. So how do we know how far each galaxy is? Well, we use there's two concepts that allow us to do this. So the first thing, if we want to know how far away something is that's emitting light, it's pretty easy to do that if you know how sort of intrinsically luminous it is, how much light is coming out of this thing. Then you can measure how bright it looks to you and infer a distance from it. For example, if you had this candle here and I moved it further and further away, you would see it, getting fainter and fainter as it moves further away. So if you knew like how intrinsically luminous it was, then you could infer how far away from it is. So that's nice. We can do that, but we need something that you know how intrinsically luminous it is. And so there was a real breakthrough in this area that's now about 100 years ago due to this person here, Henrietta Leavitt, who was an astronomer at Harvard. And she was observing a particular type of a very bright star that oscillates in time. It's very bright, so you can see it very far away. It's called the Cepheid star. And it gets a little bit brighter, a lot brighter, and fainter over and over in a cycle. Yeah? And for a whole bunch of these stars, she measured the period, how long the cycle took. And this is in log days, so this represents 10 years. But anyway, so this is like longer times this way, and this is more luminous this way. And they were closely related to each other. So he figured out that there was a type of star you could see in galaxies even that were relatively far away, and that you could measure something about them, how long they would take to oscillate, and then you would know how intrinsically bright they were. And then you could figure out how far they were. So that gave a way of measuring the distance to galaxies. And then, so that was a standard candle. Unfortunately, she passed away not too much longer than this, and left it to Hubble to pick up and build on that to yield the Hubble law I'll talk about in a second. So that's the concept of having a standard candle that you can know how far away. Now the other thing that we use is the Doppler effect. What's the Doppler effect? So the Doppler effect is when you have something that's emitting, in this case sound, and it's coming towards you. So let's say you're hearing a sound, and the thing that's emitting is moving towards you. Then those sound waves, they're compressed in front of it, and behind it, they're stretched out. Yeah, so maybe you heard like a race car go by, and it goes like, it's coming, and it's like, as it goes by, then it goes from the high to the low pitch. That's because when you're in front of it, it's pushing those sound waves together. You hear a higher pitch, and behind it, they're stretched out. You hear a lower pitch. And actually, you can figure out how fast this car is going to measure how much is this shifted to higher versus this shifted to lower. Well, you can actually do the same with light. If you have light where you know it's color. And the interesting thing is that every type of atom has its own unique fingerprint in terms of the colors of it. Here, all these colors look kind of blue. But anyway, so take any atom, a hydrogen atom, nitrogen atom, whatever your favorite atom is, and it will emit in certain very particular blue, a certain shade of blue, a certain shade of red, a certain shade of green. And we know what they are for every single atom. And so for any object out in space, we can go and look and say, oh, we expected this particular pattern that has to do with helium or hydrogen. And we saw it, but just like that sound wave is shifted to higher pitch or lower pitch, these wavelengths of light, colors that we see, get shifted to redder colors or bluer colors, and they tell us if this thing is moving away from us. Okay. So this is just illustrating that. This is the colors that go with one particular type of atom. And if it's moving away, they get shifted this way to redder colors. If it's moving away faster, they get even redder. And if it's moving towards us, they go this way to bluer colors. Those redder colors are longer wavelengths of light. And bluer colors are shorter wavelengths. These waves are getting stretched out. Okay. So Hubble put these two things together, and this famous plot here, where he took for a whole bunch of nearby galaxies, measured their distances by using those Cepheid stars, those ones that tell you that you can use to measure how far away they are, and how fast they're moving away using that Doppler effect, and saying, hey, for this galaxy, it looks like all the colors of this atom are shifted somewhat. Is it moving away? How fast is it moving away? And he put those two things together and was able to show that the further away the galaxy is, the faster it's moving away from it. All right? And we understand this as the whole universe expanding. So the more distance there is between us and a galaxy, the faster it's moving away due to this overall expansion. Okay, so we take advantage of that to figure out how far all of these galaxies are. For each one of these, we can take the light that we see, we can spread it out into all the different colors. And we could ask the question, oh, are the colors shifted redder, and how much are they shifted redder? That'll tell us how fast it's moving away, which will tell us how far away it is and hence what time it is. Okay, so people with me so far? We have a way of measuring how fast things are moving away. That tells us the distance, and that tells us the time. And so we can go and for every single one of these, spread the light out into all its colors, and then say, now I have a way of saying, yeah, those are the galaxies that are far away. Those are the ones that are telling us about very long times in the past, and some other fraction of them are telling us about galaxies that are less in the past. We can reconstruct the whole history of how things move. Right? So we have this way to do this history of galaxies just by looking and spreading out light and saying, which are the faraway ones? Which are the ones that are moving away faster than therefore? So this is just one slide telling you a little bit about what that overall history looks like, so you can know that. You know this plot is a little bit, I'll tell you what it means in a second. So up at the top, you have the history of the universe in just one slide here. From the Big Bang, over here, things were relatively smooth. There weren't any galaxies, there weren't any stars. And then for some time, about 100 million years, there wasn't much going on. And then small galaxies started to form, stars started to form in relatively small galaxies compared to what they are today. And they built up and bigger and bigger over time. Then for the past, I don't know, let's say, just to give a rough number, 8 billion years, you start to see this sort of disks and pretty shapes that we see galaxies. So that's the overall history. They got bigger and bigger, and with time they started out as sort of small, more randomly shaped things, and got into bigger, more orderly things. Now, what is this funny plot that I put down here? So this is a plot. This is time again going this way, just like it's here. And what it's showing is the rate at which the universe was able to make stars. It was making stars. And how fast was it making stars? Was it good at making stars at different times? So this is, way back when. This is here we are today. What this is showing is that on early times, the universe got better making stars. It not only started making bigger galaxies, but it started building up the stars faster and faster and faster. for about 4 billion years. And then it reversed itself and started to be less good at making stars. In fact, right now it's forming stars only about a tenth as fast as it used to way back then. So that's the rough history that we learned by doing this exercise. We learned that galaxies built up, they became bigger, they became more orderly, and that somehow this thing turned around. So we feel like we know a lot. But there's more to this story. Sometimes we see things that initially don't look like galaxies at all. They were discovered in the 60s. This is Guillermo Haro, he's a Mexican astronomer. He was cataloging a lot of blue stars, and he found some objects that were just really weird. They were blue, really weird. And then this man here, Martin Schmidt, who unfortunately passed away earlier this year, he discovered what they were. And what they were is something like this. This is an artist's rendition. Okay? But what's going on here is you have a black hole. It's at the center of a galaxy that's much, much bigger. And this is a black hole that's growing. It happens to have a lot of material around it, and it's sucking in a lot of material. Now, of course, you can't see inside of the black hole when it's black. But around it, actually, the fact that it's sucking in all this material is going around so fast heats this up a lot. This gets super, super, super bright. So what Guillermo Haro was seeing in some of these things that he thought were blue stars were actually these disks around black holes in the middle of galaxies that were super bright. So bright you couldn't even see there was a galaxy there. They outshone it by a ton. Yeah? And so amongst, if I go back to a picture like this, amongst all these galaxies, once in a while you'll see a thing that looks like, I don't know if this is, just imagine this were one. It'll just look like a point, but very blue. And you'll say, what's that? It's one of these, we now call them quasars. That name comes from quasi-stars, because originally people thought them. Well, there's a whole story to do with quasars, but it's a different one than the one Ed and I want to tell today. So I'll just focus on what you can do with them. I'm going to skip over here. So what is this a picture? This is maybe a little bit different than what you're used to looking at, but what's plotted here? This is a wavelength. So this means that these are red colors and these are blue colors over here. Okay? So things that are moving way faster, like over there, and things that are moving way less faster. And this is plotting how much light we're getting from one of these quasars. I've taken the light from a quasar and spread it out in all these different things. Okay? And you see, like, over here, you have just all this, like, going up and down. What's happening here? There's, like, light missing. There's, like, light missing here, light missing here, light missing here, light missing here, light missing. What's going on? Well, what's going on is that between us and this very bright quasar here, this black hole that's actually creating a bunch of material and shining really bright, there's some stuff that's not moving away as fast as the black hole, since it's not as red, right? So we're over here on the blue part, the stuff that's not as far away, not moving away as fast. And it's absorbing some of that light. Okay? And the exact wavelengths that are absorbing depend on the material that cloud is made of. But there's these things that you don't see emitting, but if you look at something really bright, really far away, you see that, oh, they're in the way. There's some stuff in the way. And you can figure out what it's made out of and how fast it's moving and hence how far away it is. And so what's going on is, if you have enough of these quasars, what you start to realize is that what you're seeing as a galaxy is only a small part of a bigger system that looks something like this. So here is that disk of gas stars, that you see as a galaxy. And here is something much bigger, say around 10 times bigger, that is invisible to emitting, but if you have something behind it so over here, if you had, say, a quasar over here, you would see that there was some gas between you and it. And you could trace out this thing that's not emitting, but it's still visible because it takes away light from other things, right? And if you do that enough time, you realize what's going on here is much bigger than this disk. There's gas that's accreting down onto the disk. There's gas that's being ejected up out of here into out of the galaxy. It's recycling. There's all these motions that are going on that are an intricate part of this whole story that I told you, galaxies building up bigger and being better to form stars at certain times. Okay, but as you know, as in the title of the talk, this is invisible to you. We call it the name that we give it is a circumgalactic medium, but I'm just going to call it the helium. And so, yeah, I'll just quickly show this slide. I'm going to have one more, and then I'll turn it over to Ed. And so what you can do, this is now done with the Hubble Space Telescope in this example, is you can pick a galaxy that you're really interested in, and you can look for these quasars behind it, and then do this with a whole bunch of different galaxies, and look for the footprints, the special patterns of light associated with different atoms. So this is hydrogen, this is magnesium, this is oxygen. And then you can trace out the state, how much material you have, what different elements you see, and whether it's moving forward or towards you along all these sight lines around you. And in this way, by looking for this absorption line, this light that's missing, you can trace out this larger medium that is a lot like our atmosphere. So you can imagine, thinking that the surface of the Earth is the full story, but there's this larger atmosphere that's largely invisible, and we nevertheless have a way of tracing out around these galaxies, right? And so now what I want to do is turn it over to Ed, who's going to tell you about how we move from plots like this, which show us, hey, we have this much hydrogen, magnesium, oxygen 6, to build up a picture of how these galaxies and these invisible halos are evolving together. I don't know if you can switch it over to Ed.
Okie dokie.
If you switch it so that he can control the slide.
All right. Can everybody see this? Okie dokie. First off, thanks for having me. Also, it is late here, so if I yawn, that is why. So like everyone was saying, this halo of gas is very dynamic, and when we observe it through these through this quasar absorption technique, we're only getting a snapshot of the whole picture. And so modeling this halo helps us to understand how it evolves over time, which helps us understand how the galaxy in the center evolves over time. So just a quick review of what Evan covered. Visible galaxy is huge, more than 50 million times bigger than our solar system. Beyond the visible galaxy is this large halo of hot gas with colder clouds that are swirling around it. And it's around 10 times bigger than a galaxy. And this cold and hot gas can mix and intermingle. And we use the light from these active black holes, these quasars, to observe these halos as that halo gas absorbs some of that light from that background quasar. So where I come in, so when I was at ASU and kind of continuing this on now, essentially I stir really hot gas. So we stir some hot gas with this input of energy, and what this does is generate turbulence in 3 dimensions. And this encourages the mixing of energy, heat, and mass, which is very similar to what we think is happening in this halo of gas around galaxies. I also shine some light on it. And that light has an actual source in reality where there are many quasars out there in the universe, and their collective light shines on these halos and actually heats that gas. And so you want to capture that influence in these models. And the model that we used tracks the cooling and the heating of these atoms over time as it evolves. And for the visual learners, this is essentially what I do. Take some background radiation field and shine some light on a box of gas that is turbulently stirring. So first, what is turbulence? A lot of times people might think of on an airplane where the plane starts to shake up a bit due to the turbulence when the pilot says up, buckle in your seats. But that is not what I'm talking about. What I'm talking about is the random motions of particles. And capturing this behavior is important for understanding how that invisible halo of gas evolves over time, because it's going to be mixing. There are going to be a lot of these random motions, and that's going to be influencing the gas that exists there. So when we first started doing these simulations, we started out tackling the simple case of akin to looking at patches within this halo of gas. So here on the right, I'm showing a quick little movie of one of the slices through the simulation domain. This is happening in 3D. So as you see, that turbulence is getting stirred, and we have neutral hydrogen blobs moving around as it's heating up, cooling off, and mixing. But of course, we can do better than this. This entire halo of gas is a very dynamic system. And so instead of looking at these patches within it, why not do the whole thing? So how does one start a galaxy simulation? We start with a bunch of math. We want to back up real quick and kind of tell a quick history of just how simulations got to where they are today. Initially, this is how it started. We write out equations that describe these systems, equations that we think are relevant, give the relevant physics for how this situation should evolve in time. But of course, we only have that static picture painted by the math. And then as time progressed, computer technology got better. This is an old computer in one of the NASA centers. And back then, computers would take up a whole room, and they would be, now our cell phones are more powerful than these computers were. So these computers were great for their time, but even with those, we couldn't do the types of simulations that we wanted to do and that we can do today. And so now, as time goes forward, we have these huge supercomputing complexes. This is a picture of the NASA Pleiades supercomputer. I use these to do the original simulations I showed earlier. And we have systems of these supercomputers being built all around the world to handle these powerful calculations that we want to do to evolve the universe in time and see how it might change and get to the state that we observe today. And so with these supercomputers, I'm showing we can do simulations like this. This is not one I did. This is from the Illustrious group that runs these giant universe-sized simulation boxes. And so we can run these simulations and get an idea for how a galaxy like our Milky Way may have evolved over time. In the lower right-hand corner here, you're seeing what that would look like in the visible starlight if we were observing this hypothetical galaxy. And in the middle is all the gas. And we can see that all this gas finds its way into the center, and it's playing it forward in time. And as the gas comes in, it mixes with the cloud of gas already there, makes its way into the center where it can finally join the disk and go on to form stars. And you can see some other objects coming into that halo and how it interacts with all that gas. And so this is a very dynamic system. I just love watching these types of movies. And yeah, so yeah, we can see like as this moves further and further time, that halo is kind of calmed down now. You see a spiral disk structure is more prominent in the center. There's less material flowing in and out, but even so, very dynamic. Oh, we have another neighbor coming on in to join the galaxy at the center. So galaxies come in all types of flavors. And when we first wanted to move from these smaller scale simulations to looking at the halo as a whole, the first question we asked is, okay, what type of galaxy do we want to model here? Because depending on the type is going to dictate the conditions at which we model that system. And so on the left here, I have these elliptical, which are called non-star forming galaxies. These are galaxies that aren't actively forming stars that rapidly. They don't really have that spiral disk shape to them. And then on the right, you have a spiral galaxy like our Milky Way. It's forming stars. And although they're not forming stars as much as they used to in the past, they're still actively forming stars to this day. And so we set out to model the type of galaxy we saw in the simulation before, spiral galaxy, which means that most of the energy that we want to inject with this turbulence has to come from the center, which is where those stars are going to be forming. Those stars are going to be releasing a bunch of energy and influencing the halo of gas around it. So this is kind of what we started with. The top is showing density, on the bottom is temperature. And you see in the little box there, 30 kpc, that is the size of the disk of our Milky Way. And so I want you to keep that in mind as far as the size scales go. And this black ring is just kind of help you identify the extent of this halo of gas. And so we begin it where we have most of our mass is concentrated in the center, and we start at one uniform temperature, and we inject the turbulence strongest in the center to simulate that star-forming galaxy environment. And then we just play it forward in time and let the gas cool and heat as it would. And we come back 3 billion years later, and it looks very different. There are structures that have formed within the halo, small clouds and filament structures that are there. And these clouds and filament structures also are colder than the surrounding ambient gas around it. And so we found that the strong turbulence that is injected near the center sets up this flow in the halo where hot gas is able to rise out to further distances away from the central galaxy and be replaced by cooler inflowing material. So we also wondered, okay, what if the turbulence feedback is too small? So here I'm showing neutral hydrogen. And what I've done is these simulations are happening in 3D. And so what I've done is collapsed one of those planes down. So you can see the total amount of neutral hydrogen in the box. And so if there's not a lot of turbulence being driven from the center, that means gravity can do its thing and pulls the cold gas towards the center. And there's not really any mixing between the hot and cold stuff. And that's not reminiscent of what we see in actual galaxies when we get these quasar absorption studies. Whereas if we inject a lot of turbulence in the middle, that sets up this hot halo of gas with cold gas embedded within it. And those hot and cold structures can mix and lead to some interesting structures that can form within the halo, which is more reminiscent of what we're seeing when we get these snapshot images, or not images, but absorption from the quasars behind it. Oops. And here's just a movie of that playing forward in time. So as this is evolving forward in time, we have density on the left and temperature on the right. And you can see that the initial turbulence sets up these what we call eddies, and cold gas cools near the center where most of the gas is, And you can see these cold, dense structures that form within this halo and are making their way towards the center amidst the hot atmosphere that characterizes the CGM, or the halo of gas, as a whole. And like everyone was saying, this is pretty similar to Earth's atmosphere. At least when I first saw, that's what I thought about, where we have, you could think of the water on the Earth's surface evaporating out into the air, into the sky, and then over time, those water droplets can condense, form clouds, and then rain back onto the Earth's surface. And similarly with the simulations, we have this hot halo atmosphere, and cold clouds can eventually build up within that atmosphere and then rain back down on the central galaxy to go in and make planets and stars and everything we see around us. Another thing we also wonder was, how do different ionization states compare? So these are different elements, magnesium, oxygen 6. These are elements that are commonly observed using this quasar absorption technique. And magnesium 2 is magnesium with one of its outer electrons removed. And oxygen 6 is oxygen with 5 of its outer electrons removed. The more the more electrons you remove from an atom, the more energy it takes to do that. And so the oxygen 6 is tracing hotter material. And you can see that the magnesium 2 tends to trace the densest stuff. If you remember the neutral hydrogen plot, the magnesium 2 tends to come along for the ride with the colder, denser gas. Whereas oxygen 6, you can find it not only within and embedded within the cooling gas, but also it traces the hot halo itself. And so if we can compare that to data, because at the end of the day, simulations are cool, but we have to always link it back to the data to see if we're going in the right direction or not. And so when we do that, again, we have magnesium 2 on the left and oxygen 6 on the right. And the y-axis is showing the amounts of those elements, and the x-axis is distance away from the central galaxy, shown there. And the shaded region is showing all of the different sight lines within our simulation, whereas the black points are showing Hubble data from a recent Hubble observation study that was done using these quasar absorption techniques. And the green solid line just shows the average of all the data. And so we can see that for the average of magnesium 2, it drops off very quickly, especially once you get out to past 50 kiloparsecs. But there's still many different sight lines that are out there beyond. Most of these sight lines belong to that filamentary structure we saw before we were visualizing this data. And each of these black points overlaps with sight lines within our simulation. And instead, if we look at oxygen 6 doesn't decrease that rapidly, because we saw that it traces the ambient halo as a whole. And so we can look out far out into the distant halo of gas, and there's still oxygen 6 there, and that matches the data as well. So this turbulent feedback is doing a good job of getting us closer to reality and setting up a realistic environment around a star-forming galaxy. So we wanted to take these models a step further and add some more realism in these simulations. And we did that by looking at considering magnetic fields and rotation. So why magnetic fields are important. I have another simulation to kind of demonstrate that. This is another simulation from the illustrious group going forward in time. And this is showing the magnetic fields. So regions that are bright yellow are regions associated with a high magnetic field energies. And then regions that are dark purple, not so many, not really strong magnetic fields are there. And the regions that are bright yellow also coincide with places that you see galaxies forming. And you can see that the magnetic fields overlap with those galaxies. And as these galaxies evolve over time, those bright yellow regions of high magnetic fields just get brighter and brighter, while the gas in between them, not so much. So all these magnetic fields are going to be dynamically important to how that halo evolves around that galaxy, and have a great influence on how the different elements mix, and as well as how the galaxy in the center evolves over time and what gas can make it into the center. So it's important to consider these magnetic fields to understand the influence that it has on this halo. And by now, these galaxies are very bright yellow, so have a lot of strong magnetic fields there within those galaxy systems and the gas around them. So we can make our simulations a bit more complex. And we do that by, we have the same setup as before, but this time we add in halo rotation, such that the gas around the galaxy is rotating with some initial velocity. And we also have magnetic fields, which, like I said, are going to be important for how that gas evolves over time, especially because the atmosphere of that gas is very hot. And if you have hot gas, especially with incoming radiation, it's going to be ionized, which removes some of those outer electrons. What you're going to end up with are electrons, which are negatively charged, and then a leftover atom that's going to be positively charged, which are going to follow along those magnetic field lines and be influenced by what that magnetic field does. So here I have an example of two situations. These are face-on density slices through the middle of the simulation, so we can see all the action that's happening there. And on the left is the magnetic field case. On the right is the non-magnetic field case. And I have a little black arrow at the top to show the direction of rotation. And this is going to restart again, so no worries about that. So as this evolves over time, you're going to notice some differences that arise between the two simulations. One of which being the non-magnetic case tends to develop these more clouds that are dispersed throughout it. The filaments, the cold dense filaments that build up around the center tend to get broken up more when there are no magnetic fields to hold them together. Whereas in the magnetic field case, you have more coherent dense gas that is staying together as this system evolves over time. I'll just let it play till the end of the 9 gigayears again. So we can also look at this from the edge-on perspective. So again, magnetic is on the left, non-magnetic is on the right, and the arrows are showing direction of rotation. And this time it's from the side through the middle. And this time we're looking at temperature. And you're going to notice a consequence of the dense gas kind of staying together in the magnetic field case is that there's less mixing between the cold and hot gas, which leads to an overall hotter halo of atmosphere compared to the non-magnetic field case. Also, another thing you may notice, especially towards the end, is that the non-magnetic field case tends to develop a flatter central disk structure compared to the non-magnetic field case. We can also look at how that halo magnetic field grows. So here I'm showing a face-on slice of the magnetic fields. And I have this little white circle in the middle to show that I'm not considering that region. That will be where the central galaxy is. And this plot on the left, or on the right, sorry, is showing the average magnetic field in that halo. And you can see that in the beginning, it has a steep or sharp rise in magnetic field strengths. It's because that turbulence is twisting those magnetic field lines, generating a lot of magnetic energy. And then as it evolves over time, as this halo settles, those magnetic fields tend to drop off and saturate back down to their original values that we started at. We can also look at where the magnetic field is located in reference to the matter. So the top row I'm showing neutral hydrogen again, and on the bottom row I'm showing the magnetic fields. And we can see in every case that strong magnetic fields are typically associated with denser, more wherever there's more gas at, which is traced by that neutral hydrogen. So wherever there's material, there's going to be magnetic fields along with it. And we can also compare the non-magnetic and magnetic field case from a face-on perspective and from an edge-on perspective. The top row is showing you non-magnetics, and then the bottom row is showing you the magnetic field case. And we can already see a lot of differences are between the two, where without magnetic fields, this cooling gas tends to break up more easily into these smaller clouds. You see a bunch more of these smaller clouds dispersed throughout the halo in the top row pictures compared to the bottom row. We also find that the magnetic fields help to facilitate the formation of a flatter central disk, which we can see from the second column. And finally, those magnetic fields tend to not only facilitate a flatter central disk, but also lead to a central disk that rotates faster than the non-magnetic field case. So to conclude, things we learned the galaxy has this invisible halo of gas that surrounds them. This medium is important to how that central galaxy evolves over time. Gas can flow inward and outward and be mixed. And it's where gas is recycled from the central galaxy. And all these processes have an effect of mixing the hot and cold gas, which leads to turbulence. And that turbulence gets us closer to understanding the observations. We also saw that magnetic fields do weird things. They help to protect the cold clouds from mixing with the hotter gas around them. And this also results in a flatter disk structure that spins faster than the non-magnetic field case. And overall, this halo connects the central galaxy to the rest of the universe. All the matter within our galaxy came from gas beyond it, and it had to flow through this circumgalactic medium to eventually wind up here. And then everything is connected. It's just a matter of what scale you want to look at. Simulations are all cool, but to connect this to the bigger picture, I have one last one to show everybody that just kind of zooms in on this structure. So here's from this is showing the dark matter density zoomed out super far out. And this is just zooming in to showing you the different scales. And this is gas temperature. And eventually it's going to make its way to the galaxy scales and then zoom on out again. And as it does this, it's going to transition to showing different things like gas metallicity, everything heavier than hydrogen and helium. See that concentrated to the galaxy itself. And then stellar light. If we were only looking at stellar light, the picture is kind of boring. We don't see as much stuff around the galaxy. We miss out on a lot of information of what's happening there. And then we can zoom on back out again. And so, yeah, while all these galaxies are very far apart, it's all connected through this gas in between galaxies. And throughout time, this gas can mix. This gas flows within galaxies, gets ejected from galaxies, from quasars or supernova that may be happening within them. And yeah, it's all a matter of the scale that you look at. And at the end, it's all connected through this dark matter web structure. So thank you. That is all I have. This is a summary slide just here again for you all to see. And yeah, happy to be here.
Excellent. Hey, thank you. Hang on just like you are there. We're going to just take some questions. And so again, we can do live questions from the audience. And in order to do that, you need a microphone so that the people online can hear you. And I have two questions that came in kind of during the program. Let me just kind of start with those first. One is from Stuart Shupak. He says, what is the density of the halo that surrounds galaxies, and how does it compare to the density of star gas within a galaxy?
Oh, that's a good question. So within a galaxy, the density of the gas So it looks like space is empty between the stars. But it does have a density. It's around 1 particle per cubic centimeter. Just one. But that's about 10,000 times higher than it is out in this halo of gas around the galaxy. So it's about 1 particle in 10 to the 10,000 cubic. But still, that seems like almost nothing, but it's still, when you add it up over these large distances, it acts like an atmosphere.
The second question came in a little bit later. It's from Lance Levon, and he says, what generates the magnetic fields?
Can I answer that, Ed?
Oh yeah. So whenever you have a gas that is ionized, so negative charge or positive charge material, as they move through space, that's going to generate your magnetic field. So these two processes kind of go hand in hand.
Excellent, thank you. I had a question, and I just wanted to add, do you use galaxies at a certain distance? Do they have to be close enough for you to see this, or does anything count? Galaxies very near us or very, very far away?
Oh, that's a very good question. The thing that determines which galaxy you can look at is actually that whole expansion of the universe. So if you go to, well, so there's certain colors that you can see from the Earth and certain colors that our atmosphere is actually opaque to. And if you want to look too close, a lot of times you'll be looking for absorption that is of wavelengths of light that you can't actually see from the ground. So it depends on, what data you're trying to understand. If you're trying to understand data that's taken from ground-based telescopes, you usually have to apply that to galaxies that are further away. And if you're working with the space-based telescopes, you can try to interpret and look at data that is for galaxies that are close.
So thank you. We have a couple questions in the audience here. I'll let you use my microphone. Do this one and then you.
Is there any thought in the distant future of capturing some of this energy and some of the gases for travel in the multiverse?
Well,
for our own use.
That's a very, do you want to try that one, Ed?
Yeah, that's a good question. Maybe in the very far distant future, but it would be better to look to the gas kind of within our disk. So yeah, because it's just much closer, it'd be a much easier thing to accomplish. So yeah, I mean, first thing we have to the far future, we have to be able to get to the nearest star. Was that Proxima Centauri, I believe? And getting there, that'd be a huge accomplishment already. So yeah, that'd be interesting though.
So how would the halo of gas be affected if there were two galaxies near each other enough that their gravitational pulls affected each other?
Evan, do you want to answer this?
It's up to you. I don't know. Should we just alternate, I guess?
Yeah, that's fine.
Well, that's fine. So actually, that's a very interesting question, right? So we don't fully know that, but some things that would be going on are, of course, you have the halos of the galaxies that are colliding with each other, just like the galaxies themselves. And also, when galaxies do start to go around each other, that's when the gas gets really disturbed. It drives star formation. So you'd have a lot going on. You'd have these halos themselves colliding, and you'd have the galaxies doing a lot all at once. So I don't know. That's something we could think about trying to simulate. You do have examples of that, but pretty complex. It'd be pretty interesting.
We have another audience question, then I have some follow-ups online.
Mm-hmm.
Oh, I was just wondering if the last simulation that was played where they went into the galaxy level and then back out, was that web that was at the end, is that the cosmic web? Is that what that is?
Yeah. Yep.
Yeah. That's all.
It was a great talk. Thank you. Like, this is my first talk here in the space and exploration, so it was pretty cool.
Nice.
I have a very chemistry background, so it's a most like a chemistry question. Do you think this turbulence between that's happening in these hells or the formation of galaxies, because turbulence has so much energy, do you think there is a connection between the fusion process that's happening in the center of these galaxies between those atoms and the energy being provided by this turbulence?
I guess it's my turn. So it does have a lot of energy. It doesn't have enough energy to fuse atoms together, but it's interesting that you said that your background was in chemistry. What it can do is the bumping together of atoms can take electrons away and add it onto different atoms, as you probably studied in your chemistry class. So like all those ionization states, how many electrons each atom has, change a lot because of the turbulence. And in fact, one of the things that Ed spent a lot of time on when he was developing this was including those whole changes that happen, chemical changes of losing electrons and gaining them when all this turbulence is going on. That was a big part of his PhD work.
Interesting. Thank you.
Thank you. Let me come down. I think we got a couple more. There was a follow-up question by Lance, and he was the one that asked the question about how the magnetism is generated in the first place. And his question is, to create a magnetic field, doesn't the electron motion need to be coordinated? Otherwise, the local fields around a particle will cancel out.
So what it does end up being that you have these electrons moving in a coordinated direction, like you were saying, because eventually they become tied to the magnetic field. So yeah.
We're going to kind of go to the last question here, and it's online. It's from Phaedra, and it is, she's questioning just how you describe your graphs, or many of the graphs showed scale that went from little to a lot or cold to hot. Is there a precise scale for those graphs? And I guess my question to add to that, why didn't you use a precision scale? Was it just enough to do colder, hotter?
Oh yeah, yeah. They do have a precise scale. I just changed it to that for public interpretation. It's usually easier to use, hot, cool, cold versus the actual numbers, because unless you have context to that number, it may not mean much to a person. But for context, the halo itself, the atmosphere of it, tends to be around a few million Kelvin, while the cold stuff tends to be about 100 times cooler than that. So about 10,000 or so Kelvin. And then, like Evan was saying, density wise, the ambient gas tends to be about 1 particle per 10,000 cubic centimeters, while your denser portions can be maybe 100 times that density.
I like the hotter, cooler, and that's
Yeah, it's still 10,000 degrees.
sounds great.
I guess it's an Arizona thing.
Well, thank you guys. Could we have one more big round of applause for both Evan and Ed? Ed, I think it's got to be a little bit after 11 where you are. Is that right?
Yes, it is. And I am tired.
Thank you very, very much for both of you, and Ed especially sort of like to stay up late and kind of share this with us. It's amazing stuff, and thank you very much. Everybody, we wanted to just give you a heads up about an event coming up. On October the 15th is a Saturday. We're doing a thing called EC Day, Earth and Space Exploration Day, and it's during the day. It's from 10 o'clock until 2 o'clock. There will be many, there's over 20 exhibitors that are be tabling in the areas around the lobby and outside the building, and there's 3 3D shows in this particular room you're seeing here. So mark your calendars for, it's a week from tomorrow, Is that right? No, a week from day after tomorrow, Saturday, October 15th. And thank you everybody for coming. Thank you. And thank you, Ed.
Bye. Hey, I'm on the big screen.